All right, so this is section 4.2 in the Red Stewart Calculus textbook, Calculus 30. We're talking about local max and min values. And I'm going to do a combined lesson 4.2, 4.3 in this video. So it's going to go by pretty quick. It's going to be kind of a summary lesson. But let's first talk about local min and local max values. So local, what is local? Well, when we talk about local, what we're talking about is an immediate area. So I have these green rectangles here on this graph, and as I zoom in, you will see that this rectangle would represent sort of this local area for this graph. Now this point right here that I'm circling, that would be a local maximum point, because all of the y values just on either side of that point, they're all lower. So that is the biggest y value in this immediate area. So this is a local maximum, okay? So this is going to be really big, but if I say local max right here, and you'd use the y value, I guess, for that maximum value. Now, this is obviously not the largest value in the whole graph, as you see in the picture, but it's local. So this is a local minimum, because as you see, this is the lowest point right here, local min. Okay, and up here we have another local max. Okay, so that's what local min and maxes are, local, and they're also called local extrema or relative extrema. So that's just a note down here at the bottom. I'd like to know in your textbook you might see this. Okay, now local means that we have the function exists on either side of these points as well. So that's another thing that makes local local. For example, local extrema cannot exist at the end points of the graph. So for example, over here, this cannot be a local maximum because there's no graph to the left here. So it has to have values that are clearly either greater or smaller to either side of the point in order for it to be a local max or min. Okay? So that's local max, local min. Now we talk about, there's also absolute maximums and minimums. So the absolute, obviously we have a relative extrema here, relative here, local, local here. But the endpoints are also included if we're talking about absolute. That's the absolute largest y value of the function on the entire interval. Okay, on the entire interval. So in that case, we have to consider not only the locals, but the also the endpoints. So these are endpoints. And this right here is f of a, right? If that's a. This is b. Then this value right here, this y value, would be f of b. And we have to consider f of a and f of b if we're considering the absolute, right? Because they won't show up as locals. So we have to include the endpoints if we want to find the absolute max or absolute min values. Okay, so absolute max and mins can exist where the derivative is 0 or at an end point of the interval. So let's say, here you see how this is a local and an absolute max right here, this value, see? It's both. So wherever the derivative, and I drew that black line there, that's a derivative, that's a slope of 0 on that, that tangent line. So wherever the derivative is 0 could be a local or absolute max or min, and the endpoints could be absolute max or mins. Those are the only consideration for those. Now, we could have local max or mins at undefined, where the derivative is undefined. So those areas, all right? And I want you just to watch over here. So this is obviously a local max, okay, at this point here. Maybe we'll call that x1. There's a local min here at x2, a local max right here at x3, and a local min here at x4. Now, right here, this is a cusp, and also this could have been something like a corner, right? Like that. We've talked about these before in math. But at a cusp, okay, this is not differentiable, but it is defined at this point. The function is defined at this point, and it is continuous at this point. Okay? So when we talk about f prime of x, we look at where it's 0, but also where it's undefined, because this is not differentiable here at this x5. It's not differentiable here, or it's not differentiable here. There's no derivative value. But, this could be a local max or min, such as in a cusp or a corner. So we look at the derivative where it's 0, but also where it's undefined, cusps, corners, those kind of things. Fermat's theorem, okay? In the red Stewart calc, page 173 if you're looking. So this is what Fermat's theorem says. If f has a local max or min at x equals c, and we use c because we have a new name for these values, and I'll talk about that in a second, then the derivative is either equal to 0 or does not exist, or is undefined, as I just mentioned. Now, the reason why we call these special values c is because we're going to call them now critical numbers, okay? So critical numbers are where local max or mins, or absolute max or mins could exist, okay? Critical numbers. And critical numbers are defined as the x values that make the derivative equal to 0 or the derivative to not exist. Those are critical numbers. So back here, these x values here, these are all critical numbers where the derivative is 0 or the derivative does not exist, okay? Okay, so this doesn't mean that every critical number is a max or min. That's important too, because let's see, this is a critical number right here because derivative is 0. Critical number here because derivative is 0. Critical number here because derivative does not exist. Critical number here because it's 0. Critical number here because it's 0. Critical number here because it's 0. Critical number here because the derivative does not exist. Okay? Now this can be considered over here. This can be considered as a local max. But there is no local max or min here, right? None. So we have to be careful about, defined, undefined. This is an undefined derivative, and so is this. But one can be a local max and one cannot. So we have to be careful when we examine that. But there's some, that's talking about the critical numbers there, critical values. Okay? What's the procedure for finding absolute max and min values? Okay? Well, if we look at the graph, it's easy. The highest point would be both a local max, probably, if it's not an endpoint. So it could be local max and absolute max. So y equals 6 is our absolute maximum. But consider this, y equals 1 is our absolute minimum. And so what we have to do is, and this is summarized in the textbook, we have to find all critical numbers, and we have to also consider endpoints. And so we do f of all critical numbers, as well as f of a, which would be kind of our, like where this would be a, the beginning of the interval right here, and b, the end of the interval. We also have to consider f of a and f of b as well. So when we consider all of the critical numbers, the endpoints, then we evaluate all of the y values and we pick the absolute. So for example, this is 3 for this one, not an absolute but a local. This is 2, not an absolute but a local. This is 5, not absolute but local. Actually, sorry, this 2 is not local. But these would be the ones in consideration for absolute max or mins. Okay, so again, because this is kind of a review video, I'm not going to do all these questions, but I'm going to show you how these questions were done. So I'm just going to run through this real quick. So if you have an example like this, and again, if you want to try this, pause the video right now, write the question down, and give this a try. Okay, you might not be ready for that yet, but you can certainly do that at any point in these videos. So example 6 says, find the absolute max and min values of the function. So again, as we mentioned, we want to find critical numbers, and we also want to consider the endpoints. So how do we find critical numbers? Well, the first step is taking the derivative. Once we find the derivative, we factor as much as you can, and find out which x values cause the derivative to be 0. In this case, we use the zero product principle. And I see that x equals -3 causes this to be 0, and x equals -1 causes this to be 0. So here's a critical number 1, critical number 2, endpoint 1, endpoint 2. We have those 4 values we need to plug into the original function to find their y values. And once we do that, then we just consider all of these, and we notice that this is the absolute smallest value. So there's an absolute minimum at y equals -2, or you can also write it as f of -1 equals 2, like that. That's very complete. And there's an absolute max at y equals 18. That's the max value, which is also f of 1 equals 18. So notice that this was an endpoint, and this one was a critical number. So that's finding absolute max and min. All right. So that's basically all we did for that 4.2 lesson. Now 4.3, these are very closely related, both of these. So local max and also an evaluation of the derivative are what's key to these two sections. So we're going to talk in 4.3 about the first derivative test. So the first derivative test, first of all, what we need to remember is that from 4.1, we noticed that positive slopes for tangent lines over an interval, or on a consistent sort of interval here, if all the slopes are positive, then that means the function is increasing. Okay, you remember this? And if all of the slopes are negative over an interval here, that means from here to here, that means the function is decreasing, and so on. So that's going to be very important for this section. So combine that with the fact that, hey, I know that this is a critical number here, and I know that this is a critical number here. Well, now you're going to be able to draw a more complete understanding of what this graph looks like, and be able to identify some local max and mins and that sort of thing. So the first derivative test. Okay, here's what it says in the textbook, and here's also a visual to go along with it. I'm going to show you. I'm going to try and show you both here, because I like the visual a lot. It makes a whole lot of sense here. Oh, that's too small. Okay, let me just go over the visual for you. So the first derivative test says that if the derivative changes sign from positive, and it should go through, well, most of the times it's going to go through 0. I guess we could have a cusp, right? That's the one example, the one counterexample. But it usually goes through 0 and then to negative. If that happens, such is the case in this example right here, see, positive, 0, then negative, we have a local maximum. That's exactly what the wording says up here. Okay, changes from positive to negative at a critical number, then f is a local maximum there at that critical number. Exactly what it says. If the derivative, the sign of the derivative goes from negative through 0 to positive, or from negative to positive, chances are you're going to have some kind of local minimum right in between there at that c value. That's very, very important. And this is the bulk of the first derivative test right there. Now, if the derivative does not change, as in this example, okay, we have a positive slope, and somewhere around here we do technically have a 0 slope for a tangent, and then a positive, so positive to positive, there's neither a max or min. And same is the case if it does not change, but stays negative throughout an interval. There's no max or min there. So it's the change in the sign. You see that? That's the big thing, change in sign. And so the third point says if it doesn't change at c, then there's no max or min there, okay? So this is the first derivative test. All right, so if we look at this, and I'm going to identify some critical numbers. So there's critical number 1. Here's critical number 2. Here's critical number 3. All right, so we have a 0 here. That's great. I have a positive derivative here, and on the other side of that critical number, I have a negative. So going from positive to negative is a local max, okay? So the derivative of x is positive. Then it goes to derivative of x is negative, less than 0. And here's a local min, okay? So I'll change colors here. So negative 0 to positive, see? Negative to positive, that's a local min. So f goes from negative, or less than 0, to positive. We have a local minimum. And here, again, this is positive, and then through this c, and then it's negative on the other side. So technically, we have positive going to negative, so that counts as well. Even though this is not differentiable, but as long as it's continuous, then we do have a local max there at the c. Okay? And I mentioned this already, if the signs don't change. Now watch this. If we have what if we have an asymptote here? Okay? Well, the signs, they're positive here and positive over here. So the signs technically don't change here, so we don't have a local max or min. Okay? All right. Now this question right here, if we're given this equation of a function here, and you're asked to find local max and min using the first derivative test, then what we do is we first take the derivative. Okay, that's always first. Take the derivative. Then we're going to factor that derivative. We're going to, if we can, and then we're going to find critical numbers. Okay, find critical numbers. Now there's no endpoints, there's no domain listed, so there's no endpoints to find. Then what we're going to do is we're going to do sign analysis, okay? Sign analysis on, sorry, you can't see some of that. Sign analysis on the derivative. So once we've factored it, sign analysis on the derivative. And then we're going to use the first derivative test. Okay, first derivative test to determine where the local max and mins are. Okay, state local max mins. Okay, so why don't you go ahead and give this a try. You know how to do all this stuff. So pause the video right now and give this a try. Follow the steps there I have on the right, and I'll show you the answer in a minute. When you're done, you can check back in. All right, so hopefully you've had a chance to give this a shot, and let's see how you did. So what we want to do is we want to take the derivative of this g of x function, which the derivative looks like this, right? Use your power rule, sum difference rule. You know how to take derivatives now. We're going to factor this derivative. I took a 4x out. This trinomial here, it looks pretty straightforward. We can factor that as well. So I have 3 separate factors. From this, I can let each factor equal 0 and find my critical numbers, 0, 4, and -1, according to these factors. So those are the numbers that I'm going to put on my number line when I do sign analysis, -1, 0, and 4 in that order. So if I list my factors on the left here, I'm going to find the 0, plot the 0, you know, sign analysis. It's negative on the left, positive on the right. Oh, what happened? Something disappeared here. I'll write that back up there. And then you do sign analysis, and you're able to now find what the derivative looks like as far as the derivative sign, positive, negative, and 0. Okay, so here, if we have a negative slope for a derivative, and then I have a 0 slope here, then I have positive slope, well, that looks an awful lot like a local minimum, and that's what the first derivative test says. You have a local minimum at x equals -1, so local min at x equals -1. Also over here at x equals 4, okay? Negative, 0, positive. So that's a local min too. And this over here, we have a positive, and then we have 0, and then we have negative, don't we? So that is also, well, if I can continue this graph here, that's a local max right here, okay? And so you put that together, and it would be important to also plug your x values into your original equations or functions to find the y values. So you can state this as a point, or make sure you have the y values to state their max and mins, okay? It would be best actually to write this as, just like I have here, f of -1 equals 4 is a local min, and f of 4 equals -129 is also a local min, and so on. All right, so that's that question. I hope that you got through that okay. And yeah. And so really, I do have a couple more examples here, so I would encourage you to, well, let's take a look at this one for sure. This one's a bit tricky. Why don't you do the same steps, and I'll just copy them again over here. I had to shrink them. Let's copy that. So there's the same steps to finding your local max and mins using the first derivative test. Oh, what's wrong with my computer?
Okay, so there's
So, wait. Uh-oh. There we go. Come on now. Be nice. Be good. Okay. So there's your steps. I'll make those a little bit bigger so you can see them, all right? Why don't you try that for this second example? All right, so let's see how you did. Okay, so the derivative here. Now, the derivative here, this is quotient rule. Unless I guess you want to turn this, unless you want, let me get my marker out here. Unless you want to turn this into y equals x to the -2, which honestly, I'd probably rather do the power rule than the quotient rule. So if you want to change this around, then your derivative simply becomes -2 x to the -3. See that? Probably best to write this x to the -3 with a positive exponent so you can see here's the derivative. All right. So what do we do for sign analysis? Well, you do want to put both the -2 and the x cubed in your sign analysis chart. We do have to remember though that we're dividing by the numbers here that are associated with x cubed. So I usually put a little dotted line or something in between to know that it's this number divided by this number down here, okay? So when we do sign analysis, you should get that your derivative would be positive to the left of 0. 0 is a critical number. And it should be negative to the right of 0. And because we're dividing by 0, the derivative is definitely undefined here, okay? So it's not differentiable at x equals 0. And you can see this is what the graph actually looks like. It looks like this, 1 over x squared. So you can see at 0, there's an asymptote there. It's undefined. The other thing that you want to make sure you note, if you get a critical number here, okay, x equals 0, and you notice right away that 0 is not part of the domain of the original function, you got a problem, okay? So it looks like we're not going to have a local max or min. So be sure to check that c is part of the domain of f of x. If it's not, then it's not a critical number and the first derivative test fails. So you would say, hey, critical number 0, but hey, wait a minute. Well, it's a critical, technically it's a critical number, but there's no max or min there, okay? So then this critical number causes the first derivative test to fail. I think we probably should adjust that, but you know, the critical number is where the derivative is undefined. So yes, x equals 0 is something that you should consider. But when you notice that we have undefined derivative there, you get a problem. So no local max or min, okay? All right. Well, that's all I have for lesson today, or some suggested homework. And if you do remember to go over to mrmathwell.com, and I have all of the videos. I'll have this one up shortly, and some homework there and different things for you to consider viewing and trying out. So it's mrmathwell.com. Okay, hope you guys have a great day.